No, no. It's okay, it's great. Yes, you can speak freely.
Okay. You can hear, right? No, there's one. Okay? Fine, it works. Okay, so she will use it a few more minutes and I'll give it on.
Hi, Donald.
Yeah.
Say. Oh, it's very clear. Donald, can you hear me?
Yes. Yes, I can hear you. You can hear you.
Yeah, who's chairing the session?
Sorry?
Who's chairing the session?
Myself and Vanish.
Okay. I'm asking how's the weather here?
Everything's under control, no problem. Shalom, brother. As young as you are.
Okay, how is the river there? The 50th?
Yeah, it's sunny.
No, we're asking. How is the weather? Is it sunny? Is it raining? What's happening?
We are all at the beach. What you see is just a movie. We pretend that we are doing the conference. We are all at the beach.
I cannot.
We are here.
I cannot.
Ali and all the boys and girls, they enjoy. They had too much wine last night. Knowing you are the first speaker in the morning, we knew we need some fun. Don't worry, it's a beautiful sunny day. But it's so early that you'll have a full talk.
I feel miserable now. It's raining here. It's very cold. I guess I'm probably the only person awake in the radius of like 5 miles around here because for me it's now 1:30 a.m. Outside out here at 9 p.m. there is no, everyone is in bed.
Well, I'm working for the organizers. I say the rule is when you come to Turkey, you don't stay in Brookhaven. It's much better in Turkey, right? We have a great conference, great people, good fun. You can discuss science, and Brookhaven is just doing the experiments. You don't agree with it.
I wish I no.
Huh?
I wish I would have been there.
Yeah, no.
Okay.
Anyway, Ivan will still do the bell because some people are outside, so I'll get the people inside. Of course, few more minutes, yes, okay, thank you. We have special bell for you. It's just so good. Thank you. So good morning, everybody. Can you hear me? I guess you do. And we are getting another microphone. Ivan, is the line okay?
Yeah, I
Can
can
you hear us?
hear you.
Okay, thank you. So this morning, without further ado, it's my great pleasure to introduce a friend of mine, Ivan Bozovic, whom I know for so long that I can't even remember when we exactly met. But the point is that I'm chairing this session in a very friendly way because we are now in the middle of the conference and we now need more friendly discussions in depth. So Ivan will set the stage because he's also in advising committee and he is also in the organizing committee. So feel free to attack him after the talk or in special cases even during the talk because this is the idea. The idea is that we get science going. So Ivan, I don't want to do an introduction. You're in Brookhaven, United States. Unfortunately, he couldn't fly because they have some DOE meetings and whatever. So yours is the stage. We are on time, and hopefully we hear you very well. Thank you, Ivan.
Okay. Good morning, everyone. I'm very grateful to Professor Oli Gencer for giving me the chance to meet you at least virtually and tell about some physics that I find exciting personally. In this talk, I will largely stick to overdoped quantum strontium cuprate since it is supposed to be very simple. Our people are telling us that there is just one relevant electron band and one large Fermi surface more or less around and centered around the endpoint. And if that's true, then the physics should be pretty simple and easy to understand. The normal state should behave as a Landau Fermi liquid. In what follows, I will simply call it Fermi liquid because we don't know of any other. The transport properties should follow these well-known laws due to Grover, Lorentz, etc. The point here is that some of these are actually much more general than the others as they follow from the electrodynamics of the gas with charged particles or even liquids or solids, meaning that these laws cannot differentiate between a Fermi liquid and, say, a Bose metal. The Fermi statistics enters only through this relaxation time tau, which is determined by the metric part and the Fermi velocity, which in metals is very high. In lanthanum strontium cuprate, the Fermi velocity is perhaps a million times higher than the drift velocity with the typical fields that we apply. And that means that the electron distribution is perturbed very, very little, and then we have the lattice loop, etc. Now, if the normal state is a Fermi liquid, then the superconducting state should be BCS. This works in both directions, but BCS theory postulated the Fermi liquid normal state up front. And Brookhaven has proven the opposite, that if you have a Fermi liquid and you cool it down at low temperatures, it develops some instability, and this is actually the hallmark of the condensation in the BCS superconducting state. You can read this backwards in the sense that if for some material you can show that the normal state is not a Fermi liquid, then in the superconducting state it cannot be BCS, and the other way around. And this is exactly what I will show you next. So let's start with the superconducting state. Several years back, we published a paper in which we presented a very detailed and quantitative measurement of the magnetic penetration depth as a function of temperature and doping. One key finding was that as the carrier density increased, the superfluid density decreased. And although on edge it was as low as 1% of the normal state, normal total carrier density, and then it went all the way to zero at the dome edge. This is quite extraordinary and to this day not understood, despite a lot of effort. Note that at the same time, the superfluid density temperature dependence remains linear. all the way to Tc. And so you don't see, characteristic drop due to the closing of the superconducting gap. And in fact, the more overdoped you go, the more accurately linear it gets, and down in some cases, down to less than 1 Kelvin. And this is what one should expect from an ultra-clean D-wave superconductor. Now, I'll get back to this point later on here. The other point here is that the superfluid density and Tc, they track one another as a function of doping. This is also quite extraordinary because the zero temperature superfluid density in standard superconductors is equal to the total carrier density. In other words, it is the normal state property. It's independent of the strength of the pairing interaction. And hence, in the VCS theory, superfluid density is unrelated to Tc. In contrast, in Bose condensation, Bose-Einstein condensation, that is driven by kinematics, which means that Tc is determined by the Boson density alone. Now, note, however, that there is latest theorem that applies equally to both VCS and BEC, because in the two-fluid model, as temperature goes to 0, there are no excitations left, only the superfluid. So this is actually a very big problem to think about. And for us to be sure, we double-checked it and triple-checked it by several other techniques, one of which was the peripheral spectroscopy. And this experiment all showed the same thing. In older CUPRATES, as temperature goes towards 0, only a fraction of carriers is in the superfluid. And this fraction F can be as small as just a few percent of the total carrier density. And the remaining 1 minus F electrons behave more or less Fermi-like and do not seem to participate in superconductivity at all. Now, the same was seen also by ARPES, STM, specific heat measurement, etc., while adding some more details to the picture. In VCS, as you increase the temperature, the superconducting gap should shrink and close at Tc. But in CUPRATES, that's not the case. Instead, the gap fills in from below, which means that there is always a significant metallic density of state even at 0 bias. And this increases with temperature. This can be fit well with the phenomenological Dice formula, in which the real energy is replaced by a complex number. But note that this is very unorthodox. It is beyond the standard textbook quantum mechanics. And the eigenvalues of Hermitian operators are real. So this also calls for some deep thinking. Okay, so one more probe was the short-time spectroscopy in high Tc tunnel junctions made of one-photons and CUPRATES superconducting electrodes. The short noise spectroscopy is arguably the most direct probe of the charge of mobile carriers. You may remember that Laughlin got the Nobel Prize for predicting fractional charge excitations in the quantum Hall effect only after charge 1/3 was observed by Monte by short noise spectroscopy. In Latin strontium cuprate, we observed charge 2e, the pairing, but up to temperatures that were way above Tc. And even more extraordinarily, we see pairs also at bias voltages which can be 2 or 3 times larger than the apparent superconducting gap. I don't know what this means, but what we do know that this is nothing like VCS. Now, the normal state is, in fact, all but normal. For one thing, resistivity can be linear in temperature very accurately. This was known already in 1987, but remarkable, it remained true till today. what I'm showing here is a quantum strontium cuprate field, a very good one, grown by atomic layer by layer molecular beam epitaxy. And as a figure of merit, you can use the residual resistivity ratio, the ratio of the resistivity at room temperature over the extrapolated zero temperature resistivity. Here it's more than 200. And for those who synthesize samples, by this figure of merit, this is very, very better than any bulk quantum strontium cuprate single crystal. Now, this temperature dependence is obviously unusual. As I mentioned, in Fermi liquid there should be a T-squared term due to electron-electron scattering, as it is dictated by the Fermi statistics. Only electrons from the device shell, which is KT, brought near the Fermi surface, participate. And then there must be a T to the fifth term due to electron-hole scattering. And clearly at high enough temperature, these high power walls must overwhelm any linear T-linear scattering. But they do not. And neither T squared nor T to the fifth power is seen up to 1000 Kelvin. When you compare this to 10 Kelvin, that's 100 times more. So the ratio of the T to the fifth term versus T-linear term should have grown by 8 orders of magnitude. But we don't see any of that. Moreover, the Ioff-Feregeli limit is exceeded actually by a large margin. And that's why cuprates are called bad metal. This is called the bad metal behavior, meaning that the Ioff-Feregeli limit is exceeded. Obviously, the mean-free path cannot be smaller than the distance between the atoms, so this means if just the Fermi picture breaks down. The electron motion is actually diffusing at these high temperatures, and the velocity becomes small and basically equal to the drift velocity, not to the Fermi velocity. In some sense, the behavior, the absence of saturation at low temperature is even more puzzling. What we have here is the opposite problem. Fermiology gives us the mean-free path that appears unreasonably long, couple orders of magnitude larger than the average distance between the strontium dot ions. That's less than 1 nanometer at this doping. And strontium is 2+, while lanthanum is 3+, which means, and the screening along the C-axis is very poor, so this is very much a charged impurity. So we would have to conclude that electrons which are charged do not scatter on charge defects. And that's of course hard to reconcile with Fermi liquid physics, and this indeed was recognized by all leading scientists in the field, though many of them proposed various explanations, one more exotic than the other. But so far, I don't think there is a clear winner, and certainly there is no consensus. So what it seems fair to say that this problem is still fully open. Now, we can learn more from the magnetic resistance, and in particular from scaling. By scaling, we can reveal a hidden symmetry in the data. Think of a potential of a point charge. It's a function of x, y, and z. But because of spherical symmetry, the potential is constant on every concentric sphere. In other words, you can express it as a function of only a single variable, which is radial distance out. So something like this here, when we plot the contours of constant resistivity, their shape is actually very telling. And what I'm showing at the bottom are 4 scaling laws. The first one is what you expect from Fermi liquid, and then the other 3 would be like marginal Fermi liquid, the scaling proposed by Jim Analytis and Schechter, and the last one is a sum of the magnetic and thermal energy. And clearly this last one is the winner. It looks the closest to the data. Now, I want to make here a couple of key points. The first, every one of these, Fermi liquid and non-Fermi liquid alike, satisfies the Color's rule, as I have shown explicitly at the very bottom. But the observed scaling is the one that we see is very much unlike the Fermi liquid. And second, the linear addition is suggestive of friction in a hydrodynamic fluid due to energy dissipation on whatever excitations are there. And third, note that this doesn't follow automatically from the strange metal temperature dependence. We normally assume that the relaxation time is intrinsic. In other words, that it doesn't depend on the electric field, like in Ohm's law, or magnetic field. But here, it seems that it does. So I would call this double strange. There is more in the normal state that is quite extraordinary. One of these was the observation of spontaneous transfer of voltage, something like a Hall effect, except we see that in zero field. This is not an experimental artifact. We have ruled it out by extensive experimentation for well over a decade on a couple thousand devices. We observed it for the first time in 2006, but we published it only in 2017, after we have seen it in thousands of quantum stones and cuprate devices and without a single exception. So this is an intrinsic electronic property of quantum strontium cuprate. Note that the transport is electronic, while all these films are strictly tetragonal. So that's why people call this electronic nematicity. It's breaking of the rotational symmetry of the crystal in the electronic fluid. And I should also say that the orientation of the high conductivity direction is not pinned to any of the crystal axis, and it can even rotate as a function of temperature. All of this proves that this is purely electronic effect. It doesn't come from the lattice. And it is so extraordinary that so far there has been no proposed theoretical explanation that I'm aware of. Now, one of the most positive aspects here is that we see that everywhere in phase diagram except for the extreme overdoping and all the way up to the room temperature. Now, this means that this order is very strong and robust. And we have tested this by some new experiments that actually corroborate this. With John Chapman at St. Buffalo, we were studying dipolars in quantum stones and cuprate films, terahertz, far-infrared, mid-infrared, and nematicity is observed at frequencies from millimeter waves up to mid-infrared, which means up to hundreds of milli-electron volts. So this is indeed a very large energy scale, implying a very strong driving force. At this point, I would like to mention that after our 2016 paper that showed the demise of superfluid density with overdoping, many explanations were proposed. The majority of these actually speculated that this is somehow due to this solid, one way or another. And indeed, the thought did occur to me early on, but did not seem very likely, simply because the coherence length in CUPRATES is so short that most of the CUPRATE samples are in the clean limit. You will need this order that is significant of the scale of 1 nanometer and then goes to much denser than that. Well, in some sense, something like this was seen by STM already 2001, 2002, showing days reported incredibly large variations of the react by up to 300% and varying on the scale of just a few nanometers. And that's where we have another puzzle or paradox. In my group, as I said, we can measure the magnetic penetration depth with an absolute accuracy of 1% using the mutual inductance technique. What you see in the real part is the Meissner effect, and in the imaginary part there is dissipative peak that occurs near Tc. And the point here is that in our best film, this peak is very sharp, implying that variations in Tc are less than 0.1 Kelvin, and that's over the area of 50 millimeters squared. This is consistent with what I said earlier about the superfluid density being linear in temperature as expected in ultra-clean D-wave superconductor. To double-check this, we deliberately added some chemical disorder by doping orthomoslantine cuprate with some zinc. And the temperature dependence changed immediately to a very parabolic one, even with just 0.5% of zinc doping. That means 1 zinc atom per 200 unit cells. So if there is a very small disorder, it screams at you. You cannot just miss it. We have also done some tunneling experiment ourselves, except in SIS type heterostructures. And here are a couple of spectacular observations. You can see that these peaks are sharper than 1 millielectron volt. And note that we are averaging over 1,000 square microns. If the gap varied by 300%, it would have averaged to nothing. We wouldn't be able to see any of these features. And we are not alone in this. Here are some quite spectacular microwave data from Walter Hardy's group 2 decades ago on an extremely clean YBCO 42 crystal. The relaxation rate measured here is less than 3 gigahertz, which is something like 10 microelectron volts. And that means that the inferred mean-free path is of the order of 10 microns. That's extremely clean by anyone's standards. Now, in the last few months, we have done a new experiment that's not yet published. Here, we're looking at one and the same orthomoslantine cuprate field, but we tune the mobile carrier density by ionic liquid gating. We were able to tune Tc by more than a factor of 2. We measure the temperature dependence of resistivity and the penetration depth operando, which means as we are gating the sample, and we can change the gating and does the doping level of Tc in fine increments. So what we monitor is the residual resistivity ratio, which is a figure of merit telling how well the sample is ordered. The higher the residual resistivity ratio, the more ordered the film is. What's easier to understand is the electron mobility. So I can express this as electron mobility, and the result is precisely the opposite of what was hypothesized. As we increase the doping, both the critical temperature and the superfluid density decrease, but the mobility increases, which implies that film appears less disordered. And this is consistent with improved screening and lower dissipation rate. But how do we reconcile all this with STM results? We may get a hint from REE, reflection high energy light diffraction. This is a surface-sensitive characterization technique that we use to monitor the film doped in real time. So in fact, we watch REE movies. I watched that movie more than 5,000 times so far. And what I always see is this, some extra sidebands in between the main streak, which are 0th, 1st, and 2nd order drag reflections. These sidebands show that there is a surface reconstruction. The unit cell at the surface is enlarged, typically 4 by 1 or 5 by 1 reconstruction. And that's after coupled deposition. But note that this superstructure was never observed in the bulk. So the surface is different from the bulk. And this is not a surprise. The opposite would be very surprising. In ionic crystal, like in CUPRATES, the cohesion energy is modeled, which is very long range. We can feel it over 40 and 80 unit cells. An ion in the middle of the sample sees ions opposite charge above, below, left, right, behind, and front. But on the surface, half of that is missing. So the modeling energy is much smaller, and for that reason, the unit cell in ionic crystals close to the surface expand. And also ions move laterally, and if there are volatile species like oxygen, then it simply diffuses out, etc. In short, in CUPRATES, the surface is always different from the bulk, crystallographically, chemically, and electronically. Now, a couple of words about interactions. We all know that the current lanthanum cuprate compound is antiferromagnetic, and it harbors magnons as excitation. But the question is that bulk. How about lattice? We know that in almost all known superconductors, lattice is the main player. We addressed this question through a pump probe experiment in which lanthanum cuprate film was excited by light pulses from a terahertz laser and probed by ultrafast electron diffraction. So the electric field was the light was perpendicular to the film surface on a couple of oxygen plates. The electric field is in plane. But as a response, we saw that the film blew up, expanded along the C-axis by as much as 2 or 3%. Now, this may look small, but for crystallographers, this is colossal because the lattice expansion from 0 Kelvin to melting point is something like 1%. So what this means that there is extremely strong coupling of the motion of the charge in plane to the displacement of the ions out of plane that are nearby, as indeed you have to expect in an ionic crystal. Now, what I wish to show here is a new experiment which is even more spectacular. Again, this is spectroscopy of SIS junctions with lanthanum strontium cuprate electrons. The area of this is something like 1,000 microns squared, the area of the barrier. But you see very sharp features in the IV, DIPV, and the second derivative. The second derivative here is measured directly, but we also measure the first derivative, and then we can do the second derivative numerically, and they all agree. So what you see here are these periodic features which are called the vibronic progressions. They come from when quasi-particle is excited above the gap, then it interacts strongly with lattice and emits multiple acoustic phonons. So such vibronic progressions are very rarely seen, in particular, with this many oscillations, and they are known as a hallmark of strong electron-lattice coupling and non-adiabatic physics. I won't have much time to talk about other cuprates, but let me just make a general remark that most of what I said applies to all of them and is actually universal. They are all strange metals, meaning that the resistivity can be linear in temperature at some doping levels, and in several cases this linearity persists down to the dilution fringe temperatures, few tenths of millikelvins. And the field that are tested are also what I have called double string, meaning that the resistance is also linear in the magnetic field. I have mentioned already the strain dependence of Tc on the zero temperature superfluid density, which is essentially linear but with finite offset, except very close to the origin where it turns to a square root dependence, as one would expect from quantum critical phase fluctuations. Well, almost identical dependence was seen in a different cuprate by VCO, by a different group, using a different technique. Moreover, it was on the heavily underdoped side, while our LSE is on the overdoped side. So the point is that it appears that, as Jan Zanen would say, there is some very powerful and simple principle at play. I would like to end up on a high note, and for any clinical work, it should be the prospect of some real-world electronic applications. Some years back, our claim to fame was the discovery of interface superconductivity. We used two materials, underdoped lanthanum cuprate and heavily overdoped lanthanum strontium cuprate. So neither of these is superconducting per se in isolation, a single phase. But when we bring them together into intimate contacts, then high temperature superconductivity magically appears, and it can be as high or even higher than in any single phase lanthanum strontium cuprate. We invented a neat new trick that we call zinc delta doping tomography, by which we were able to determine where this interface superconductivity resides. Zinc is known to be a very efficient poison for superconductivity in cuprates, even at very low concentration. So we use zinc as an atomic marker, in the sense that we dope zinc in a single copper oxygen plane. That's what's called delta doping. And then we make a series of samples like this, and in each sample we dope a different copper oxygen layer, and that's the tomography aspect of that. So what we found is that both in resistivity and in nuclear inductance, Tc stays basically undiminished, meaning the resistivity and superfluid density, except in one sample, and that's the one in which zinc was doped in the second lanthanum cuprate layer after the interface. So in this way, we were able to prove that interface superconductivity is confined to a single copper oxygen layer, which makes it the thinnest superconductor known. And yet the Tc is about the same as in the optimally doped lanthanum strontium cuprate. Now, new is that we leverage these earlier discoveries to do something useful. And this was to atom such lanthanum strontium cuprate bilayers into nanowires. They are maybe 100 nanometers wide, but just a couple of angstrom superfluid thickness. And that means that the cross section was several hundred times smaller than what was achieved before. And these tiny nanowires act as single-photon detectors, and these single-photon detectors have greatly increased operating temperature compared to the currently used low Tc single-photon detectors, and they also operate at much higher frequency range. Here, what is shown was the test at the commercially important telecom frequency, which is 200 kHz. And this illustrates how our advances in basic science led to real application. Note that superconducting nanowire single-photon detectors are already used en masse by NASA for astronomy and probably by other agencies for other purposes that I don't know. I was told that 10 Kelvin difference in the operating temperature makes a difference of 1,000 in the thermal budget, and not to mention the reduction, the complexity and the size, which becomes critical if you want to send it in space or put it into mobile robots and some such. So these high Tc nanowire single-photon detectors are really promising a breakthrough in quantum sensing, imaging, and communications. It's time to start wrapping this up. I hope that I have made a compelling case that the field of high temperature superconductivity in CUPRATES is full of accumulated evidence for very strange phenomena in behavior that beg for a consistent and all-encompassing explanation. Some new physics is hiding here, and we need to unravel it. And I think that when we do, we'll know that instantly. I think Einstein said that when you stumble upon the truth, you will know that right away. Moreover, I think this will be some kind of an enlightening eureka moment after which we will see much further and deeper. And for this reason, I maintain that unraveling the mystery of high temperature superconductivity in CUPRATES remains one of the most important open problems in physics today. Thank you for your attention, and I'm welcoming any questions you may have.
Thank you, Ivan. Please notice he's even on time for questions. So now we have the shooting to ask questions. Ivan, you're right. We will arranging microphones and checking who is asking question. Don't frighten. Come on, early morning. Shall I bring you cognac or
It's
coffee?
40 minutes, so there should be some
frightened. Don't worry, don't drink too much. Fine. Okay. Yep.
Hello, Ivan. This is Herman speaking. I was wondering, when you engineer layer by layer by deposition methods.
I need to repeat the question. It was noisy.
Yes, hello.
It's working.
Yes, can you hear me now?
Yeah, I can hear you very well.
I was wondering, when you engineer layer by layer these CUPRATES, for example, I guess you need to start in 3 consecutive layers.
Yes, definitely.
Is there anything you can find by going to an extreme? Or let's say, what would happen if you put 4 consecutive layers? Would that generate some secondary phase, or what would happen?
If you are talking of atomic period, like if you do quantum information CUPRATE, we will put one quantum oxide layer, one quantum oxide layer, and then we continue with that. In this way, we are maintaining the 2 and 4 stoichiometry. We are going single phase 2 and 4. We have experimented a lot over 3.5 decades with other crazy things. For example, in Bozovic series, you have higher end compounds. There is Bozovic 2201, 2212, 2223. They differ by the number of copper, oxygen, calcium layers. And the engineering this, we were able to go 2234, 2245, 22 up to 2211, 12. That's where I stop. And this we can grow. They are not stable compounds. If you take a 2234 and you melt it and you cool it down, you will not get any 2234. But we grow in molecular beam epitaxy. We have the ND window in temperature, which is maybe 100 degrees below the melting point. So there is enough surface mobility that the film grows very highly crystalline, but no bulk mobility. And that's how we create this artificial compound. So we have grown 278 and we were able to dope it and make it superconducting. We grow 1278 where we put one valence layer up and we can grow that. Not very many, it's very unstable, but we can grow one or two of these. And that also superconducting PC was about 75 Kelvin. Then we were able to grow, we tried to grow volume, Brookhaven is 3D superconductor with the highest PC, 30 Kelvin. All high PC superconductors are 2D, quasi 2D. So the question is, what will happen if we make BKB of 2D? And we were able to do that. We were able to make superlattice where we had 2 layers of bismuth oxide and 1 layer of platinum oxide in perovskite configuration. So we have 2 metallic layers, 1 insulated layer. This is 2-dimensional, quasi 2-dimensional metal. But so far no superconductivity there. And then 10 other examples. We also put different barriers when we make these tran junctions. Not only lanthanum cuprate, but we have done aluminates, zinc oxides, titanites, nickelates, cobaltates, and so on. But of course, there is a limit to what you can do. If it is really, really unstable, then it decomposes and you get secondary phase mutations. I've seen that many times. And then, we just switch the machine off and we come tomorrow again.
Okay, thank you. We have another question for you, please.
Hello everyone,
Yes.
this is Sergey Archipov.
Hi, Sergey.
My question is that after so many years of intensive research, this big list of strange experimental facts that you show us, does it become shorter or it becomes longer?
I think, I think it became longer. Some of these things are new. For example, this linear scaling with magnetic field, that's actually pretty new. Also, these vibronic progressions that I've shown you, that is so new that it has not been shown before. And man, this is like a hammer to the head. I mean, how do you explain this? Okay, so chemists know about this. People who study molecules, when you photoexcite a molecule, sometimes it will change the configuration. So, for example, benzene is flat, but if you photoexcite it, it goes armchair. So it's a different geometric configuration. And that means that you, when it disexcites, you generate, you emit a number of vibrations, quantum vibrations, quantum molecular vibrations. And then you can see these progressions riding on the electronic transition, vibronic progressions, and they are typically optically active vibrations. What we are seeing here is emission of longitudinal acoustic phonons. And I think it happens because you have, these lanthanum tungsten cuprate electrodes, and then you have charge hopping from one side to the other. And when that charge hops there, you get a charge disbalance instantaneously and locally, and that distorts the lattice, and it has momentum in that direction, so you get emission of the acoustic phonons. And we look at the neutron scattering from inelastic neutron spectroscopy, and the energies match. These are the Riemann zone edge acoustic phonons being emitted along the CX.
We have a question from Andrea Galaxy for you.
Hello, Ivan. Have a nice evening for you. Look, I have a question regarding
Can
Can you hear me?
Yes.
Yes. On the top of your list of strange properties, you mentioned the linear resistivity. However, I think the situation is even more complex or puzzling than that, because, as you mentioned, the linear behavior occurs only in some interval of doping, and the change of temperature dependence of the resistivity is really amazing. Going through the phase diagram. In the underdoped region, one finds a downward bending. In the overdoped, you find an upward bending. So I think the resistivity is really. I think one should really understand also the behavior of the resistivity in the overdoped regime and the underdoped regime.
Absolutely, and actually I do, and I have the data. I could talk about that for, if I had another hour, I could show you all of that. We have studied by now more than 2,000, close to 3,000 on-consortium CUPRATES films. We have covered densely the phase diagram. We have resistivity data, we have magnetoresistance data measured in fields up to 90 Tesla. We have Hall effect data. And it's, some several tens of thousands of data files. It's very hard to compress that in a relatively short talk. So I tried to focus here on just what is simplest to convey. And I think what I've shown is enough to wake up and tell us, there is something really puzzling here that needs to be thought of seriously and deeply. But you're right, there is much to be learned from the doping dependence, which I almost completely skipped here except for the superfluid density. To make it short, it looks like there are the best fits are obtained when you use something like a two-component model, where one component is strange and meaning linear rho versus T and rho versus B, and the other one is T square dependent, more like permuted line. And what happens when you increase the doping is that the relative contribution of one is going down and the other one is going up. So it starts looking more and more thermoelectric like. But we see these traces of this fringe component all the way up to the edge of the dome and even a little bit outside of the dome. That would be like a short perspective.
Thank you. We have one quick question and there is a coffee break, but quick, please.
Thank you very much. I have one question. Actually, I have 4 questions, but no.
Well, then write in a letter. No, we cannot do it. One question quick. No way.
And you say the superconductivity is confined to one kappa oxygen plane. And my question is, could we achieve the superconductivity just this was plane? Because in Euclides observed this ferrum selenium monolayer superconducting. And is there any influence, and where is the interface that you also said it could be reason of this such kind of enhanced superconducting? Thank you very much.
Actually, the short answer is no. And there are a number of theoretical models. I would say the mainstream thinking about CUPRATES will just consider a single copper oxygen two plane modeled by a single band, 2D Hubbard model or TJ model. Some cases, people will do 3 bands to include, hopping between copper and oxygen, which obviously is there. But in all of these cases, it's just a simple copper oxygen plane. And then they tune the doping level by changing chemical potential. But these models are not thermodynamically viable, because if you add charge to copper oxygen, you keep adding charge to copper oxygen plane and you don't compensate it in any way, then in the thermodynamic limit, the energy will be infinite. So these models are simply thermodynamically not viable. copper oxygen plane is charged. There is a charge minus 2e, that's okay. Okay, and it has to be compensated, made charge neutral. And that's the purpose or role of these 1 atom, 2 1 atom oxygen layers. 1 atom is 3 plus, oxygen is 2 minus, that's 1 plus overall. So you have 1 plus, 2 minus, 1 plus. That's your smallest charge neutral units. If you try to grow a layer that is not charge neutral, it will explode. You call an explosion. So simply ions will fly away, what will remain will be charge neutral.
Thank you, Ivan. We have to close. We really have to close because we have the sessions. So, final word.
Okay, so the short answer is no, you cannot just grow a single copper oxygen plane layer because it's not charge neutral. You need a charge reservoir layer to make it charge neutral. New will form more, which is 2 plus.
Thank you very much. Now, applause for Ivan. And now if you are good, you get coffee. If you are bad, you have tea. If you are very good at coffee, then you have sweets. Thank you very much. See you in 5 minutes. God bless you.